Hello everyone, this is the pre-launch news conference for Soil Moisture Active Passive, or SMAP. To be launched aboard a Delta II rocket on Thursday at 6:20 a.m. Pacific time. And all of our launch countdown activities are going to be discussed here today, including the flight of the Delta II and what will be happening to the SMAP spacecraft as it leaves the Delta II rocket. So we'll start our briefing first of all with some opening remarks from Christine Bonnickson, the SMAP program executive from NASA headquarters. Then we'll hear from Tim Dunn, who is the NASA launch manager from the Kennedy Space Center in Florida. Vern Thorpe, the program manager for NASA missions for United Launch Alliance, Centennial, Colorado. Kent Kellogg, the SMAP project manager from the Jet Propulsion Laboratory, Pasadena, California. Dara Antakabi, the SMAP science team leader from the Massachusetts Institute of Technology in Cambridge. And Lieutenant John Martin, the launch weather officer from the 30th Operations Support Squadron at Vandenberg Air Force Base. And we'll start first with our opening comments from Christine Bonnickson. Chris?
Thank you, George. SMAP, or as we call it, the Soil Moisture Active Passive Project, will be monitoring the water that lives and moves through the soil. Could you bring up the first slide, please? SMAP will be joining our 19 operational satellites, which along with air and ground sensors monitor the Earth's vital signs so that we can address issues like weather, climate change, fresh water, water hazards. And it's really kind of exciting that we're launching this in the UN Year of the Soil, because we have a large number of international organizations that have volunteered to support the SMAP project from countries such as Kenya, Australia, Canada, and Argentina. They are going to be helping us verify the algorithms and do data collection to support that activity, and help us to analyze the massive amounts of data that will be coming down from this satellite. Soil moisture is a key part of the 3 cycles that support life on this planet: the water cycle, the energy cycle, and the carbon cycle. And these things affect human interests: flood, drought, disease control, weather. If you would run the video, please. SMAP has 2 instruments on it: an active instrument, which is the radar, which will be providing high-resolution data, and a passive instrument, the radiometer, which provides us high-accuracy data. These 2 instruments give us a picture similar to looking through both lenses of your bifocals at the same time. So we end up with a very high-accurate global map of the soil moisture content. This dual vision activity was one of the reasons why the measurements that we're getting on SMAP was ranked so highly by the National Academies of Science Earth Science 2007 Decadal Survey. And we're really excited that we're able to launch this mission within 10 years of receiving that recommendation. This global soil moisture map will give us both the soil moisture and the freeze-thaw state of all of the moisture in our soil every 2 to 3 days. NASA is currently very focused on this launch coming up and the knowledge we're going to get from that. If you would bring up the next slide, please. The SMAP launch completes a series of 5 launches that we've done in 11 months that started with the Global Precipitation Measurement launch in February out of Japan. And we're really looking forward to the synergism of all these instruments that we've lost and the amazing knowledge that we're going to gain as we start analyzing this data. Back to you, George.
Thank you, Christine. And now to Tim Dunn, who will be the NASA launch manager for the countdown on Thursday, and from the Kennedy Space Center in Florida. Tim.
Thank you, George. I'm proud to be here today representing the men and women of NASA's Launch Services Program. I'm the NASA launch manager for the SMAP mission, and I'm thrilled to serve as launch director for a Delta II launched NASA spacecraft that will measure and map Earth's soil moisture distribution with unprecedented accuracy and coverage. my high school agribusiness teacher, Mr. Britnell, he would have loved to have SMAP's data to correct the results of my 11th grade Future Farmers of America soil judging team. After last summer's successful OCO2 launch, the launch team is back at Vandenberg Air Force Base and happy to be launching Delta II again. SMAP will launch on a Delta II vehicle from Space Launch Complex 2, the pad we call Slick 2. The SMAP mission will be the 370th Delta rocket to launch since May of 1960, and Slick 2 is proud to have hosted 82 of those Delta launches. I'd like to recognize the Delta II team. I can't say enough good things about the entire launch team for this mission. ULA, NASA, JPL, the Air Force 30th Space Wing. The assembled group of professionals that we have, they're knowledgeable, certainly competent, and they're very enjoyable to work with. I'm blessed to be able to call myself a member of this team. Over the past week, our team has been busy with many final launch preparations. Last Thursday, the combined NASA, ULA, and 30th Space Wing launch team held our flight readiness review. We assessed the preparations of the rocket, range and facility assets, and the readiness of the SMAP spacecraft. Last Friday, we performed our mission readiness rehearsal with the entire team participating. Also beginning last Friday and completing yesterday, the ULA crew loaded the hypergolic propellants of nitrogen tetroxide and Aerozine 50 on the Delta II's second stage. Now I'd like to show a video of the ULA crew assembling the Delta II launch vehicle that will launch our spacecraft from Slick 2. Please roll the tape. Here you see the arrival of the Delta II first stage at Vandenberg Air Force Base. The Delta II is assembled in Decatur, Alabama, and then trucked over the road to California. After we bring it out of its shipping container, it's taken across Vandenberg Air Force Base up to the pad. And here you see the morning of August 4th, where we are erecting the first stage of Delta II onto the launch mount at Slick 2. You'll see here we're using the mobile service tower as a mobile crane to erect the first stage. SMAP is going to fly in the 7320 configuration, meaning it has 3 solid rocket motors on the sides, or SRMs. These are GEM 40s, we call them, for their 40-inch diameters. They're made by ATK in Utah, transported here to Vandenberg, and you'll see the ULA crew very carefully and methodically mating to the first stage. The spacecraft will be encapsulated in a payload fairing. We fly a bi-sector payload fairing. That means 2 halves, and we put that into the mobile service tower clean room prior to erection. This is the second stage power plant for the Delta II rocket, and you'll see it is being erected there with the AJ-10 engine on the aft end. That will be mated to the top of the first stage and interstage assembly. Here we are, fast forward to the morning of January 13th, raising the spacecraft in its protective transportation can, and there's the ULA crew unassembling that can. And now you see the payload fairings, which were stored in the white room, being very carefully mated around the SMAP spacecraft. Here's a view of the completely mated payload fairing inside the clean room at Slick 2. This morning we held the launch readiness review, where we received approval from senior NASA and ULA management, as well as spacecraft and range agencies, to continue processing toward launch countdown early Thursday morning. At Slick 2 today, we performed Delta II range safety and beacon checks with our first and second stage engine slewing, and the final azimuth update for the flight computer. Tomorrow afternoon, we will begin final launch pad preparations at approximately 7 p.m. Pacific time, when we load refined kerosene fuel, or RP1, onto the first stage, and then move the mobile service tower away from the rocket to the launch position. The launch team will arrive on console just after 1 a.m. Thursday morning, and will perform the final preparations of flight computer turn-on and stage pressurization around midnight, followed by first stage liquid oxygen loading at 4:30 a.m. Tuesday morning. Final engine slews will be performed approximately 5:25 a.m. Pacific time, and then we'll be ready for launch at 6:20 and 42 seconds a.m. Pacific time with a 3-minute launch window. In summary, the Delta II rocket and SMAP spacecraft are ready, and the launch team is prepared and excited to be here at Vandenberg Air Force Base to launch this important mission for our nation.
Thank you, Tim. And now to Vern Thorpe. He's the program manager for NASA missions for United Launch Alliance, headquartered in Centennial, Colorado. Vern will discuss the ULA role with the Delta II and NASA, and then the flight of the vehicle. Vern?
Hey, good afternoon. The United Launch Alliance is honored to be here again 2 days before the launch of the SMAP satellite. And I'm excited to be here for this first NASA launch of the year and also for the first of our ULA launches during 2015 out of Vandenberg. Our ULA team started working with NASA to integrate the SMAP spacecraft about 2.5 years ago. We started in about July of 2014. We began building the vehicle for this particular mission in our factory in Decatur, Alabama shortly after that. And the entire time, ULA has worked very closely with the NASA Launch Services Program, the spacecraft team at the Jet Propulsion Laboratory, and with our industry partners to get us to this day. As always, it's been a tremendous team effort, and we look forward to a great launch on Thursday morning. SMAP will actually be ULA's second launch of 2015, following on the heels of our Atlas launch of the MUOS-3 spacecraft just 1 week ago today. SMAP will also be the 153rd Delta II mission, and it will be our 52nd Delta II mission for NASA. The SMAP mission will be launched aboard the Delta II 7320 configuration. That includes a first stage booster powered by the Aerojet Rocketdyne RS-27A engine, and as Tim mentioned, we'll have the 3 strap-on solid rocket boosters provided by Alliant Tech Systems, or ATK. The upper stage will be powered by the AJ-10 118K engine, and the payload will be enclosed in that 10-foot diameter payload fairing that you saw. That's a composite payload fairing. We'll use that for the first few minutes of flight and jettison that once we're out of the atmosphere. Now I'd like to show you a video of the launch sequence, and this will give you a preview of what we're going to see on Thursday morning. So here's the vehicle on the pad. We're going to lift off shortly after 6:20 in the morning. The window opens 43 seconds after that for 3 minutes, as Tim said. And the first major event you'll see after liftoff for this mission will happen when we jettison the SRBs 99 seconds into flight. Those SRBs actually burn out about a minute into flight, but we hang on to them until the predicted splashdown locations have cleared the local offshore oil platforms. So you'll see the SRBs jettison here in a moment. Once the SRBs have jettisoned, the first stage will continue to fly for a total of about 4 minutes and 20 seconds. And once we've used up the propellants in that first stage, we'll shut down the engine. And 6 seconds after that, we'll separate the upper stage. And 8 seconds after that, we will light the engine on that upper stage for the first of several burns for this mission. Now, this first burn of the upper stage will last just a little bit more than 6 minutes. Shortly into that first stage burn, we'll jettison the payload fairing, as you see here. And once we're done with that first burn, we'll be in a parking orbit. That parking orbit will last about 41 minutes. And then we'll do a short second burn followed by spacecraft separation, as you see right here. Spacecraft separation will occur about 57 minutes after liftoff for this mission. Now, when we're done with the primary mission, with separating the SMAP spacecraft, we're actually going to do a third engine burn. It'll be a very short burn, about 8 seconds, to adjust the orbit slightly. And following that, we will actually be separating 4 CubeSats. We have 3 Peapod dispensers on board that contain a total of 4 CubeSats. And then when we're done with the CubeSat separations, we'll actually do a 4th engine burn. and that fourth engine burn will burn all the propellants that are remaining in the second stage, and that will allow us to actually do a controlled re-entry of the second stage. And about 2 hours and 10 minutes after launch, the second stage will splash down in the southern Pacific Ocean, several hundred miles east of New Zealand. So the men and women in ULA are proud to serve a critical role in delivering payloads to orbit for all of our government and commercial customers. It's our honor to launch this important Earth science mission to help scientists better understand Earth's overall water, energy, and carbon cycles. And ULA always maintains a relentless focus on successfully delivering critical capabilities like this to orbit, and we are very proud to be America's ride to space. So I'd like to say thank you again to all of our mission partners. The entire ULA team looks forward to a great launch on Thursday morning. And with that, I'll turn it back to you, George.
Thank you, Vern. And now to continue with that thread of events and also talk some about the SMAP spacecraft is Kent Kellogg, the SMAP project manager from the Jet Propulsion Laboratory in Pasadena, California. Kent?
Thank you, George, and I want to add my thanks to NASA and the KSC Launch Services Program team. The SMAP project is absolutely thrilled to be catching a ride to space on the Delta II vehicle with a very long and well-proven history. So we feel like we've been in very good hands and very well treated here at Vandenberg by the teams over the last few months. I want to pick up where Vern left off by talking about what's going to happen with the spacecraft after we separate from the Delta II upper stage. So if we could run that mission animation, please. So once we separate from the upper stage will has a high-definition camera aboard that will stay focused on us for about 150 seconds after we separate. We hope in that time to be able to catch the start of the solar array deployment. Onboard sequences on the spacecraft will begin communicating back with the ground. We'll deploy the solar arrays, and we'll point the spacecraft and solar arrays toward the sun. We expect that process to be completed as early as 8 minutes after we separate, depending on the spacecraft attitude as we leave the Delta II, or it could take as long as about 50 minutes, so there's a little variation there. We'll spend the first 2 weeks checking out the spacecraft system, and then we will deploy our large instrument antenna that you see here on the screen. We'll deploy the boom first, and then 4 days later we'll deploy the large 20-foot reflector, and then 50 days after launch we will spin up the reflector to have a fully operational observatory. You'll notice the spacecraft counter rotates in the animation. That's by design because of the large spinning mass that we are spinning up. The antenna beam points off at an angle. It doesn't point directly below the spacecraft, and that allows us to map a large swath, about 1,000-kilometer wide swath below the spacecraft. That allows us to map the entire globe in less than 3 days. It's quite an efficient mapping system. Now, I've been working on this project for about 6 years now, and a lot of design and effort has gone into it. Certainly some of the science folks working on the project have invested far more time in that, 15 years and earlier and more in some cases. A lot of effort has gone into this. I want to share with you a little bit of the work. If we could roll the hardware flow video. We began assembling the spacecraft bus about 1.5 years ago at JPL. You can see here the solar arrays being deployed. This is the radar panel being installed onto the spacecraft. There's a lot of testing that goes into this. This is a spin test of the radiometer and feed horn that was done before we installed it atop the spacecraft. We go through vibration environments. We test the large antenna. That obviously got a lot of attention to make sure we had well tested that, to make sure we have a good system when we get into space. We go through environmental testing to make sure that we're going to work as intended after we go through the vibration of the launch environment, and also in the vacuum environment and thermal environment in space. So here you see some scenes of the spacecraft being put into our large 25-foot space simulator facility at JPL. And then last July, we did a final spin test of the spin platform on the observatory. And then in October, we shipped the observatory to Vandenberg. So on October 15th, we loaded the observatory into a truck, and then early that morning, it arrived at Vandenberg at the Astrotech payload processing facility, where we completed the last of the functional checkouts to make sure the observatory was operating properly after its transportation to Vandenberg. We fueled the spacecraft, went through the final checks. Everything went very smoothly. We had no issues or problems during that time. And then, as Tim described, we began the process of putting it inside its can to move out to Space Launch Complex 2. So we've invested a lot of time testing the observatory. We feel we've got a very reliable design. We've got a very committed and passionate group of people that have worked on the project over many years. We feel that we've got a lot of confidence that this mission is going to provide top quality science data for many years in space. I want to acknowledge that our mission partner here, besides JPL, who had project management responsibility, developed the spacecraft and the radar instrument, we also had a lot of support from the NASA's Goddard Space Flight Assembly that provided the radiometer instrument, science support. Both centers share in the science data processing that will be performed once we get the data flowing from space. So with that, I think we still are showing some video here. This is of the spacecraft being attached to its launch vehicle adapter at Astrotech before it was put inside the can. It was moved to Slick 2 on January 13th, so we've had a very smooth operation getting it installed on the launch vehicle adapter you see here, and getting it transported out to Slick 2. So with that, George, while the video winds up, I'll turn it back to you. Thank you.
All right. Thank you, Kent. And now to learn more about the SMAP mission, Dara Antakabi, the SMAP science team leader from the Massachusetts Institute of Technology in Cambridge, Massachusetts. Dara?
Thanks, George. SMAP is in a unique position because its measurements impact two distinct domains. One, of course, as a science mission, it impacts how we fundamentally understand how the environment works and peer into the metabolism of the environment. And second, it impacts some of the applications that touch our everyday lives. I would like to give you examples of each one of those. And to the first slide, in the area of science impacts as a science mission, the three cycles that maintain life on Earth are fundamental cycles of the Earth system: the water cycle, unique to Earth, the energy cycle, and the carbon cycle. These three are linked together through soil moisture and freeze thaw. They're like three gears in a clock. If one of them speeds up, it affects the others and has a cascading downstream effect. If it wasn't for soil moisture, these three gears would act independently and would vary without any synchronization. But we know that's not the case. As soil water evaporates, that's precipitation that has gone into the soil, so it's the history of precipitation. As that evaporates, it feeds the clouds and returns that precipitation back to the atmosphere, and you got a water cycle going. Just as humans have adapted to perspire in order to maintain their body temperatures, the Earth does the same. It takes energy to vaporize that water. So it's involved in the energy cycle. The solar radiation that's incident at the surface gets absorbed and gets released back or dissipated through the evaporation process. So that's how the water and energy cycles are intimately linked. And also plants, as they transpire, what they do is take carbon dioxide gas from the atmosphere, take energy from sunlight, and convert that into the leaves and branches that they have by releasing water vapor. So the carbon cycle gets engaged with the water and energy cycles. These three work again like gears in a clock, and they have to be synchronized. Are models of the environment, whether they're used for short-term numerical weather prediction or longer-term projections of the impacts of climate variability and climate change on regional water cycle, need to get this coupling between the three cycles correctly, and therefore need the soil moisture information that SMAP is going to provide. So that's the science impact of peering into how the Earth environment's metabolism functions. In the area of applications, if I go to the next slide, here's an example that touches our everyday lives. This is from the National Weather Service, from their website. This is the flash flood guidance. It's produced daily, and the date on the top indicates what day that was the validity of this particular map. And it's basically soil moisture deficit, how much the soil can hold beyond what the current soil moisture conditions are. And it's in units of inches. This is produced daily, updated daily, and shipped out to about 120 weather forecast offices spread around the country. The forecaster looks at this map, looks at the NEXRAD radar, ground-based radar precipitation map, also in units of inches of precipitation, and whatever the precipitation exceeds the flood guidance, immediately a flood warning is issued. Now, this map of surface soil moisture or soil moisture deficit is not produced based upon ground-based instruments that measure soil moisture around the country, because there are far too few ground-based sensors to come close to producing such a map. So this is produced by models, best guesses of what the soil moisture conditions should be any one day. Now, what SMAP will provide is exactly that measurement, but at higher resolution and directly and with great accuracy. So it's going to help improve this daily operation that goes on. In a second example, and the final example, here's at the other extreme. This is a weekly map produced by a collaboration between U.S. Department of Agriculture, EPA, and NOAA, and some other agencies. And its validity of this one is just a few days ago. And this is an estimate of drought conditions. This drought agricultural drought is defined in terms of deficit in soil moisture. So the very definition of drought is a deficit in soil moisture. And you can see the big dry in California on this map. Again, what SMAP can provide is a direct measurement of this quantity at higher resolution and from space and globally. So with that, George?
Thank you, Dara. And we'll look now at the weather forecast for Thursday morning from First Lieutenant John Martin, the Launch Weather Officer for the countdown on Thursday from the 30th Operation Support Quadrant at Vandenberg.
Thank you, George. Weather along the central California coast in January typically consists of shallow high pressure with occasional low pressure systems that transition through the region. Currently, California is seeing some of this shallow high pressure building into the region with upper level areas of low pressure skirting into over the high and causing increased cloud cover in the mid to upper levels. If we could take a look at the satellite coverage here. You can see clear skies over most of the range with the lingering upper level low causing increased cloud cover along the northern portion of the western range. The upper level feature is tracking to the northeast and is not expected to be an impact for Thursday's launch. If we could move on to the launch forecast slide. All right, so for Thursday, we are expecting another slight upper-level low-pressure system that will move over the region late Wednesday and into early Thursday morning, bringing thicker mid-level to upper-level clouds with a little bit of cirrus over the range. For T0, visibility will be unrestricted with winds out of the north-northeast between 8 to 12 knots at Slick 2. Temperatures will be comfortably in the low to mid-50s. The overall probability of violation for T0 is 20%, with the only constraint of concern being for thick clouds. If we could shift to the scrub forecast slide. Lingering moisture from that upper level low will move east of the range for Friday, resulting in thinning clouds aloft, and the thick cloud probability of violation dropping to 0% for the scrub day. Winds will shift to a northwesterly component and pick up to to around 15 to 18 knots at Slick 2, with visibility still remaining unrestricted, and temperatures will start to climb a little bit to the mid to upper 50s. Overall probability of violation for the scrub day will be 10%, with the only constraint of concern being the surface winds at Slick 2. And that is all for weather. Back to you, George.
All right. Thank you very much, Lieutenant Martin. And we're ready now to take questions. For the social media, you can use hashtag AskNASA, and we will go right now to some questions here in the room and take some social media questions. So we'll start here in the front, and please give your name and affiliation when you get the microphone. Justin?
Hi, Justin Ray with spaceflightnow.com. For Kent, I was wondering if you could explain a little bit more about how the antenna is deployed. What actually drives it out?
Okay, so the antenna has a motor actuator that drives the system. It basically unfolds like a rhombus, if you will, that moves from a collapsed state into a deployed state. So it initially blooms out. You saw in the animation right after it releases, it blooms out to about 7 to 8 feet in diameter, and then there's a cable drive system that powers it out to the remaining 20 feet in diameter. That process takes about 30 minutes in space. So we were able to show it in the animation running much more rapidly than it would in real time. When we deploy it, we would have full telemetry visibility via TDRS. We've designed that process very carefully so we can watch it. But the deployment is dealt with autonomously by the spacecraft while it's happening. So did I answer your question?
Yep. And just a quick follow-up. When do you actually expect the spacecraft to become operational?
So operational is maybe that's a bit of ambiguous. It can be an ambiguous term. We will spend 90 days checking out the spacecraft system, deploying the antenna, spinning it up, getting the instrument fully checked out, making sure all the systems are working properly. We've allowed 90 days for that to occur. After the 90-day period, we will go into what's called a calibration and validation phase. That's where we're actively using the instrument to collect data on soil moisture, and then we have a science calibration validation team that takes the data coming from the spacecraft and compares it to ground truth sensors so we can bring the spacecraft data into alignment with specific sites around the globe to make sure that we're meeting our data accuracy requirements. That soil moisture data will be basically available, not fully calibrated 6 months, 6 months after we complete the checkout period, 9 months after launch. The validated science data, calibrated soil moisture science data, will be available 12 months after the checkout period is complete, 15 months after launch.
Janine
Scully, newshawk.com. You talked about working on this program for quite a few years. How eager are you to finally get to this day and basically get to Thursday and get this process going? I'm
extremely eager. My wife is probably even more extremely eager. You work a lot of time to spend a lot of time to reach this point. You invest a lot, long hours, weekends. Everyone that works on these kind of projects is very passionate. They invest a lot of themselves in it, and it's great to reach this point. It's also a point where you're putting all the marbles on the table. This is the point where, it's like handing over the keys to your car to your teenager. You hope you've prepared them well. You hope all the lessons stick, and then you send them off, and most of the time you're very pleasantly surprised. But we're very excited, and we think we're going to have a great mission here.
And for those of us that are writing for the more general population, can you help us explain exactly why Joe Citizen should really care about this this mission?
I think, Dara, why don't you answer that?
Yeah. So what the soil moisture measurements will do is improve our weather forecasts, improve our assessments of water availability, and also address some issues dealing with long-term climate variability and assessments of the impact of human intervention in the global environment. So all of these come together, and it's the metabolism of the system, how it responds. Just like a human body, if you perturb it by feeding it something, we want to know how the entire metabolism working together responds. And that's the water, energy, and carbon cycles. This is the variable that links all of them. So whether it's water availability, weather forecast, seasonal climate forecast, agriculture, early famine warning, all these applications really depend on this key variable.
All right, any other questions here in the room? We have one back here.
If I may, thank you.
Hi, Patrick Healy from NBC4 in Los Angeles. And Dr. Entakabi, if I could follow up on that and ask you to be perhaps a little more granular. Are we talking about, in the case of flood prevention, actually being able to go to a region and telling people you should leave this area because the probability of flooding is very high? And conversely, in California, where we're dealing with this drought, are there specific decision-making data that will become available and that could be utilized?
Okay. So let me go back to the first one, the flood case. As you saw, that was a map of daily soil moisture put out by the National Weather Service. So if you have real data to test that operational product and that application, you will impact the entire operation of flood forecasting in the country. And also that applies internationally as well, which is important because it's a satellite measurement mission. In terms of drought, the very definition of drought, when you say this county is in drought condition, this one's not, is based upon what the soil moisture is. Right now, we're making that decision based upon models. This would be a direct measurement of that quantity, that it could affect things like agricultural operations, insurance, disaster relief, emergency declarations, and other activities.
All right, I think we're ready now to take social media questions. And if you do in social media have a question, you can use the hashtag AskNASA to send your question to us. And have we got questions that have come in already?
Indeed. Twitter user Kevin asks, how long will NASA SMAP be in space? So if you want to talk about the mission duration.
So I'll take that. We have a requirement to operate SMAP for 3 years. That's more of a funding, a planning constraint. If the spacecraft is returning healthy data and is useful, NASA has the option to extend the mission. Typically, these missions, can last for a decade or more, and we expect if the spacecraft is healthy, it should be capable of that. NASA has a process that they go through once we've reached the end of our primary life, that 3-year period, where they will evaluate whether they want to allocate additional funding to extend the mission. So that's we expect the spacecraft itself, though, and the instrument to be healthy and last for many, many, many years.
Wonderful. This next question comes from Amber, who asks, can you explain the use of stages in deploying the CubeSats? So if you can explain the deployment process for that a little bit.
You want to take that, George? Vern, you want me to?
Yeah, I can give it a try. Yeah, so for the CubeSats, we use what are called P-pods, and essentially it's a box about the size of a loaf of bread, a little bit bigger, and it has a door on one end, and inside you can have a small cube, hence the name CubeSats. You can have 1, 2, or 3 of those inside, and when it comes time to deploy those, we simply send a command that allows a spring-loaded door to pop open on one end of that box, and there's a spring deployment mechanism that just pushes the satellites out. So.
And we do have a briefing immediately following this one on the CubeSats, so we'll go into a little bit more detail on how that's going to work.
Wonderful. An additional question here comes from Twitter user Harris, who asks, how does a satellite that high in space accurately measure moisture in the soil underground on Earth?
Okay. That's the beauty of the microwave range, is that you can see through clouds You can see regardless of daylight or no sunlight, see-through vegetation, moderate vegetation, and the signal is sensitive to the amount of moisture in the ground. And the radiometer acts like a camera. It catches the ambient amount of radiation being emitted, but its resolution is limited by the size of the antenna. The radar acts like a flash camera. It actually emits a pulse of radiation and looks at what comes back. It has the advantage of resolution. The combination of these two is what makes the soil moisture measurements possible. Now, the pairing of these two instruments and the way they're operated are optimized for the problem of soil moisture, and that's what's unique about the mission.
All right, another question here from Twitter user Amber, who asks, how long before SMAP data will be made available, and will there be a certain NASA DAC in charge of data dissemination?
I will answer the first part of that. NASA actually chose to put the SMAP data into two different DACs, one for the radar and one for the radiometer. The National Ice Center in Boulder and the Alaskan Satellite Facility up in Fairbanks, Alaska. Kent, do you want to cover the rest of that?
Yes. So there's two answers to the question of when the data will be available. We want to give ourselves a little time to make sure that the measurements are calibrated and checked out. We'll begin releasing uncalibrated, unvalidated data 6 months after launch. That'll be the basic radar and radiometer data. The calibrated radiometer and radar data will be released 9 months after launch. And as I mentioned earlier in the briefing, the soil moisture data, the unvalidated data will be released 9 months after launch, and the calibrated data will be released 15 months after launch. Now, once the data starts flowing, it will be sent to the DAC on an ongoing basis. Every day, the satellite will download large amounts of global soil moisture data. It's pipelined directly to JPL and Goddard for science data processing, and it will be released to the DACs within a matter of 24 hours to 36 hours, depending on what level of data we're talking about. So there'll be a continuous, ongoing flow of delivered data going to both of the DACs. That's been one of the objectives of the mission, to get the data from the satellite to the DAC as quickly as we can, because we know that there's a lot of interest in having very fast access to near real-time data.
All right, we have time for one more social media question.
All right, this last question comes from Twitter user Frankie, who asks, how do you counteract the spin of the reflector?
Okay, so I'll take that. We have very large reaction wheels inside the spacecraft bus. You don't see them from the outside view, but they're basically very large wheels that spin very fast. They're like a gyroscope, and that's how we counteract the momentum of the large spinning reflector. Very good question, though. It was something it was one of the early design trades that we considered very carefully, and it's a great insight to think to ask that question. So very good.
Any more questions for media here in the room? All right, in that event, we're going to pause just long enough to change the participants on the dais so that we can discuss the CubeSats and the spacecraft that are also flying on the Delta II second stage and some of the objectives of those 3 satellites. Thank you very much.